So today we're going to start the second part of unit number 7 where we talk about waves at boundaries, and in this one we're going to talk specifically more about reflection and interference. Now waves always encounter different forms of boundaries. As they're traveling through mediums, they're going to hit different types of mediums along the way. So sound travels through air, but then it can also travel into water and through walls, which is a solid, so it has to have some sort of properties as it hits a type of boundary. And any wave, regardless of what type it is, if it hits a boundary, there's going to be two things that happen, and how they happen is dependent on the properties of the boundary and the wave. But the wave will be partially reflected and transmitted. So the best way to think about that is if you hear an echo, that's been a wave reflected off of something far away, but then you can still easily hear somebody talking through a wall, and that means that the wave was transmitted through that wall, but it's often quieter, so you've lost some of it because part of that wave was reflected. So echoes would be a good example. Talking through walls would be an example of transmission, and you can also think about waves reflecting in a pool at the sides of the pool. To draw reflecting waves, we want to think about wave fronts. So each of these wave fronts, you could think about this as a crest, and this would be another crest. So it's just like crest to crest. So each wave front shows one full wavelength. As that wave comes into a boundary and it's at an angle, it's going to get reflected. And there's properties about that. But it's difficult to always keep drawing waves as all of these lines, because they're going to start to interact with each other. So it's easier to visualize them as single rays rather than a full wave front. So much like you have done in the past with studying light, this is the same, because light can be acting like a wave. So as for any mechanical wave, we have the same properties. So with this diagram, a wave ray, so instead of a wave front, is just the arrows that represent the direction the wave is traveling. There's a normal drawn invisible. It's not actually there, but it's a perpendicular line off of the surface, and we use that to measure two values, and that would be the angle of incidence and the angle of reflection. So we use that normal value to measure the angle from there, and depending on the angle will tell us some properties about the transmission into the other medium, and we'll get to that a little bit later on. Right now we're going to focus on the reflecting part, and in terms of reflection, we can symbolize that the angle of incidence, theta I, the angle of incidence, is always going to be equal to the angle of reflection, so theta r. So those two angles will always be the same for a reflecting wave. This is used in a lot of different things, satellite dishes, parabolic microphones, and even flashlights. So satellite dishes and the microphones collect the waves coming at them, either from the satellites or just sound waves, and reflect them towards a receiver, such that all of these waves, wherever they hit on the reflector, end up pointing to that point. So they're kind of centralized. Whereas the flashlight does the opposite. It has the light source at that centralized point, so that all the waves that come off of it reflect off of the reflector, and it's curved so that it creates a beam of light coming out of it. So they use the same properties but in opposite ways to achieve their purpose. With all of these waves and going around, they're always going to be interacting with each other, and that's the most important part. How do they interact? So we have to come to interference. Waves are going to interfere with each other. If you think about being out on the water, waves are going all different directions, and you can sometimes see how they start interfering with each other, and there's some certain properties that go along with that. So we've got these two situations here. We've got two crests coming at each other. I've labeled them A and B so that we can differentiate them after. and we're going to think about what they're going to look like when they meet and what they're going to look like after. And we've got two crests and then a crest and a trough to look at afterwards. To do that, I'm actually going to pull up a simulation and we're going to visualize this on a couple of waves. So in this simulation right now, you can see a blue wave that's just appears to be traveling towards the right of the screen, and regular amplitude of about 2 squares, and it just keeps moving to the left. So I can hide that blue wave and I'll put up an orange wave that's almost the same amplitude of the wave, appears to be about the same, it's the same frequency, but it's just moving towards the left. So if we were to combine these waves, they would be moving in opposite directions, which together it looks like this, which can be quite a confusing looking diagram at once. So I'm going to posit it a couple of different times, particularly about here, where we've got two waves, the blue one and the orange one, lined up so that their crests and troughs are perfectly lined up so that they're meeting at the exact same point. When this happens, the result is this green wave, which has an amplitude of twice each of the original waves, because both of those waves are combining together. If you think about it on a rope, there can only be one visual wave. So that wave has to take both of those amplitudes and add them together. So we get twice the amplitude on our wave. And if we keep going, just in slow motion here, I'll hide the green wave. As they keep going, they start meeting at different points, where instead the crest of the orange wave is meeting at the trough of a blue wave and vice versa. When this happens, the same type of thing. There can only be one visual wave represented, and when there's a crest meeting a trough and they're added together, you get this green wave, which is a result of a crest and a trough. It's like adding a positive and a negative together, and they cancel each other out. But the question with this is what happens afterwards. So if I hide maybe just the orange wave, and we just go back to playing it, the blue wave is always part of it. It has a source on the left side of the screen, and it's going to keep going through. Just like the orange wave has a source on the right side, it has to keep going. The only reason we don't see each individual wave is because they're interfering with each other, and that gives us the result of this one visual green wave, which has twice the amplitude when the crests meet and no amplitude when the crest and the troughs meet. So let's go back and try and draw this with our diagrams. So for our first situation, we have both of our crests meeting together in the middle, and on our single rope we end up with one giant looking crest that would have an amplitude of A plus B. Now afterwards, and this is the part that's tricky to understand and visualize because we can't see these waves as different because they have the same amplitude, which is why they were labeled. So we've got one and the other, because they just keep moving. They move through each other and keep moving as if nothing has happened. So A is keeps going that way, and B keeps going towards the left. Because the waves are not affected by each other, they just, when they're in the same place at the same time, their amplitudes are added together. Now for a crest meeting a trough, a very similar thing happens. We're still going to do A plus B, but if we think of one as positive and the other as negative, we end up with a completely no amplitude wave. And after, again, they just go right through each other as if they're not there, not affected, or B keeps moving that way and A keeps moving to the right. So we have one where the amplitudes are doubled and the other when it is actually completely canceled out. The first option we call constructive interference, and the second option is destructive, which is a little bit misleading because neither of the waves is destroyed. It's just visually they have been canceled out when they're in the same place. When they're not in the same place, they're still the same waves as they were before. So to answer this question at the bottom, how does interference affect the original waves? it has no effect. The original properties are exactly the same. The frequency doesn't change, the wavelength doesn't change, the speed of the wave doesn't change, the amplitude does not change. Nothing changes when interference, it's just the waves are in the same place at the same time being added together. There's a unique, or not unique, a special situation of interference that is a very important topic in the study of music, and that's a standing wave. Standing waves come in many different forms. They can be tight at both ends or they can be open at both ends, but they're all a standing wave because they're two waves interfering, but the actual wave itself does not appear to be moving left or right. So if you think about that simulation, and I'll put a link for it for you to play around with, you can see how the green wave does not appear to move left or right, but the orange wave and the blue wave are each moving left and right. But the resulting wave does not appear to move, and that's a property used to make any musical tone. Particularly on guitars, you can change the tone of the string by changing how many standing waves occur between the point where you touch it touch the fret and the other end. And the same with any musical instrument. It's a big part of that how they're designed. So in that, the part where you have that greater amplitude, which we saw in the green wave, is called an antinode because that's where things are having, this would be our constructive interference. Constructive interference at the antinode where they're appearing to have this huge amplitude even though both waves were not individually that size. And anywhere you see that the wave doesn't even appear to move at all would be a node, and that's because at that point there's always destructive interference, which is really interesting to try and look at because it looks like the part of that wave doesn't move at all, even though the rest of it is moving significantly. Now standing waves, there's a lot more that we can talk about with standing waves and talk about harmonics, but that's something that you can look up more on your own if you're interested into the science of music and sound. And as always, so as the end of this section, we'll talk about refraction and stuff later. So as always, physics is awesome.